We are now ready to begin. We've had to let the speaker have my computer, so online people, I can't know whether you're seeing anything. So if one of my colleagues, perhaps Oliver, if you could keep an eye on things to see what's happening. So sorry about the delay, but it's a great pleasure to welcome Natasha Oughton back to come and speak to us today. Natasha read physics and philosophy at Bristol, then came here to Oxford for the MST in philosophy of physics, went on to the GPhil. Once you finish that, she's now at the National Centre for Quantum Computation, where she's the Quantum Computing Policy and Ethics Lead. She's going to be talking to us today about some of the work she did in her fascinating GPhil thesis, and here putting some shape on the shape of the question, why quantum theory? So over to you, Natasha. Thanks very much.
Thanks very much, Chris. It's really lovely to be back in this room and to see lots of familiar faces. So thanks very much for inviting me. So yes, I'm going to be presenting on some results and some arguments that I made in my DPhil thesis, which was on information theoretic reconstructions of quantum theory. And can I successfully navigate through? I can. Okay, a quick, or maybe not so quick, look ahead at what's to come. So starting off, I'll give a quick definition of how I suggest that we define reconstruction or reconstructions of quantum theory. I'll then present two case studies, so the information causality principle and the CBH reconstruction. I'll talk about the role of reconstructions more generally, so what we should be hoping to get when we carry out these reconstructions. And I'll discuss some claims, and I'll suggest that, that what we don't necessarily achieve is interpretations or interpretative insight, but I'll suggest that what we can do through reconstruction is contribute to explanations and understanding. So I'll review some of the claims made about explanation through reconstruction in the literature, and I'll then go on to propose that the best model to capture these sorts of claims is Van Brassen's pragmatic model of explanation. And I'll then extend that to a pragmatic model of understanding. And finally, I'll go back to those case studies and discuss how we can gain this pragmatic kind of explanation and understanding through reconstruction. So starting off, what is a reconstruction? So typically when we reconstructions of quantum theory start with a neutral background and impose some often physically motivated constraints to narrow down to some aspect of quantum theory. I suggest that we slightly modify a schema that was proposed by Grimbaum in 2007. So Grimbaum takes it that we specify a set of physical principles, formulate their mathematical representation, and then Grimbaum's third step is to rigorously derive the resulting formalism of the theory. Now, I suggest a slight generalization of this to rigorously capture quantum theory in the relevant sense, because I think this then allows us to talk about activity like the black box approach, which I take to be a good example of reconstruction. So on first to our first case study, so which is the information causality principle. So the information causality principle is set within the black box approach to characterizing theories, where we characterize physics in terms of input-output probabilities, abstracting away from the underlying constructive parts. Typically we approach this by considering the CHSH sum between two distant parties, Alice and Bob, and we can consider the probability of achieving the CHSH correlation, which is correlation here. So I'm sure many of us will be familiar. This is an example of a Bell inequality and is often considered in that context. So by doing the right fiddly bits of maths, we can say that classically K is bounded by 2 with access to an entangled quantum state. K is upper bounded by 2 root 2, the Seiwelton bound. But we can also note that K has a maximum algebraic value of 4. So if the correlations work in the right way. So noting this, Popescu and Rawlik ask, why isn't quantum physics more non-local? Why doesn't it violate this upper bound further? And here I mean non-local as to be Bell inequality violating. So this effectively started the PR Box program to capture quantum correlations in terms of principles. So the idea is that non-locality plus some mystery principle gets us to the quantum correlations. And the Pesquean Rohrlich's first guess is whether no signaling constrains this non-locality. But in the black box framework, we can straightforwardly see that boxes with the following probability distribution, now known as PR boxes, are non-signaling, so satisfy the relevant no signaling constraints, but correspond to the maximum value of the CHSH sum, so saturate the CHSH sum. And so that answer turns out to be negative. So since then, a program of research has started to find a principle that does arrive at the correct value for the Tsai-Wilson bound, so limits correlations to quantum correlations. And there have been a number of proposals along these lines. So the first of which being Van Dam's paper in 2005, which was published in 2013, who proposes non-trivial communication complexity. And this was then extended by Brassard et al. In 2006. Linden et al., no advantage for non-local computation, Pavlovsky et al.'s information causality principle, and Nabescure's and Vanderlijk's macroscopic locality. So these principles achieve varying levels of success in deriving the Tsai-Wilson bound. Information causality gets to the exact bound, as does no advantage for non-local computation, and non-trivial communication complexity gets close. I think macroscopic locality gets there as well. Just to flag, I won't go into this in too much detail, but just to flag that a potential challenge for these sorts of principles is the almost quantum set, which was proposed by Nabescure's et al. And this set turns out to be strictly larger than the quantum set, but is compatible with almost all of the above. So this suggests that maybe this isn't the right approach to go down, but we'll disregard that worry for now. The exception to that almost quantum result is the information causality principle, but there is evidence to suggest that this too is compatible with the almost quantum set. So the information causality principle starts with, again, a non-local game. We have two parties separated at a distance, Alice and Bob. Alice receives a string of n bits, and Bob receives a variable b between 0 and n, and the task is for Bob to guess the nth bit of Alice's string. And to help with this, Alice can send a classical message x consisting of n bits. And so the information causality principle states that the quantity of Shannon information that Bob can recover using all of his local resources, which might be correlated with Alice's local resources, and allowing Alice to communicate classically is at most m the information volume of Alice's message. So Pavlovsky et al. Choose to formalize this in terms of the Shannon mutual information and place the upper bound and constrain that with m. And the expression holds in classical and quantum theories, but is violated with access to correlations beyond the Tsai-Wilson bound. So this is supposed to be a foundationally significant reason, physical reason behind the Tsai-Wilson bound. So I won't go into the concerns too much now, although a cheeky plug that Chris and I are currently working on a paper on this, so hopefully you'll be able to read that soon. But elsewhere in my thesis, I argued that the derivation of the Tsai-Wilson bound relies on particular properties of the Shannon measure, which don't hold for other measures which we might equally well take to be reasonable measures of information in this context. So I claim that this substantially undermines the significance of the information causality principle in playing this foundational role. Other authors also derive the information causality condition directly from results on an entropy measure in different physical theories. But we might question too whether these kind of requirements on an entropy measure are reasonable to hold. On to our next case study, the CBH reconstruction. And I think many of you in this room will be familiar with this, so I won't spend too much time on it. But the CBH reconstruction is proposed by Clifton, Bubb, and Halverson, who suggest characterizing properties of quantum theory in a C-star algebraic setting. So these are kinematical independence, non-commutativity, and the existence of entangled states. And they claim that each of these are equivalent, respectively, to 3 information theoretic constraints. So no superluminal information transfer, no broadcasting, and no bit commitment. Again, just to flag some concerns, which I won't go into too much detail of, and drawing from Chris's book. So firstly, we might question if the C-star algebra starting point is sufficiently neutral. We might think that using a complex vector space already assumes too much. Evidence to that comes from the fact that toy theories like Speckens' theory doesn't start from a C-star algebra, does satisfy the CBH constraints, but is not quantum theory. Another concern we might have is the role of no bit commitment. So this was proposed to entail entangled states, but the presence of entangled states already follows from kinematical independence and non-commutativity. And the CBH actually acknowledge this, and they say that no bit commitment ensures that entangled states are introduced as part of the physical theory rather than being mathematical artifacts. But this seems to then undermine its formulation as a principal theory if we're having to put in place constraints over what exists within the theory. Okay, so those are a few examples of reconstructions that fit within the schema that I've suggested. But we might now question, what are we expected to get from these? So some suggestions that often crop up are interpretational insights, so whether we might expect to get an interpretation of quantum theory or a solution to the measurement problem, whether we might expect to gain more knowledge of laws or metaphysical underpinnings, or the conclusion that quantum theory is about information. Epistemological insights, so explanation or understanding of quantum theory, and novelty and fruitfulness, new theories or new technology. And behind these claims is often the fact that these are assumed to follow either from the principal theoretic nature of reconstruction, so the fact that the theory follows from defined principles, or to the information theoretic nature. So considering these claims, let's start off with what the role of information is in this context. I won't read these quotes out loud, but just to demonstrate the sorts of things that have been said about information. And on the other hand, we have Shannon, the founding father, potentially, of information theory. And I really like this quote. So, it will be all too easy for our somewhat artificial prosperity to collapse overnight when it is realized that the use of a few exciting words like information, entropy, redundancy do not solve all our problems. So I think we should take Shannon's words of caution seriously here. Many reconstruction attempts are information, and to kind of further add to that, many reconstruction attempts are information theoretic in the sense that they're operational. They don't place a particular importance on information as a quantity. And moreover, we choose to capture quantum theory in this way. And the fact that it turns out that we can capture quantum theory in this way, I don't think necessarily gives us motivation to think that quantum theory is about information. The way we choose to capture it in a deliberately vague and deliberately neutral setting doesn't give us reason to think that that tells us something about the kind of underpinning entities or whatever it might be behind the theory. So what about the principal constructive distinction? Can we draw on that to motivate some of those claimed roles of information theoretic reconstructions? So this was introduced by Einstein in 1919. Constructive theories attempt to build a picture of complex phenomena out of some relatively simple proposition, and the prime example is often kinetic theory. And on the other hand, principal theories take as their starting points and foundation not hypothetical constituents, but empirically observed general properties of natural phenomena, principles from which mathematical formula are deduced of such a kind that they apply to every case which presents itself. And the contrasting principal theory being thermodynamics in this case. So principal theories are often held to be advantageous where we don't already have a constructive theory, and also where we might want to reason from observed exceptionless regularities. But there are some disanalogies with the usual historical examples of distinction in the case of principal versions of quantum theory. So firstly, the order of development, special relativity and thermodynamics were proposed before a corresponding constructive theory was fully developed. But principal theoretic reconstructions followed a fully worked out quantum theory, although we might differ over whether we think it's a constructive theory. And also, by definition, the axioms or the theorems underpinning quantum theory, underpinning the reconstructions, are already results in quantum theory. So we're not necessarily getting anything new out. And there are also multiple contenders in the case of quantum reconstructions. Whereas in the case of, for example, special relativity and thermodynamics, a single candidate principal theory was a significant forerunner. And in the quantum case, we have this large number, and so again, that seems to undermine kind of privileging that theory, or undermine the motivation for coming up with it. So just to give an example of claims about interpretation through reconstruction, I wanted to briefly discuss Bubb's various arguments about interpretation through reconstruction. Firstly, in 2003, Bubb CBH make this claim that the CBH reconstruction offers an interpretation in virtue of its form as a principal theory. But as Harvey and Chris might argue, and Oliver and Chris too, principal theories don't tell us about the dynamics, and so you might worry that they don't provide an interpretation in this sense, that telling us about the kinematics alone isn't sufficient to provide an interpretation. Bubb's second and third attempt at arguing for this claim that the CBH reconstruction offers an interpretation is to argue that since the CBH reconstruction reveals that quantum theory is about information, or assuming it does, then interpretations of quantum theory are empirically equivalent, and therefore we shouldn't question, and therefore we don't need to ask for an interpretation. It's wrong to ask for an interpretation. But as Chris points out, and as I pointed out earlier, why should we assume from an information theoretic reconstruction or an operational reconstruction that quantum theory that's captured in terms of information is about information? Moreover, recall from those principles in the CBH case that they don't refer to information as a kind of physical thing out there in the world. They capture things in terms of information theoretic possibilities or constraints. The final attempt, or not the final attempt I'll discuss here is Bubb and Patowski in 2010 claim that the information theoretic structure of Hilbert space kinematically constrains possibilities, and therefore this avoids the need for an interpretation. But this doesn't mean it's unreasonable to ask for a dynamical or a constructive account or an interpretation that tells us what the world is like. Telling us what the constraints are doesn't preclude us from asking what the world is made up of, what things are hitting each other, those kinds of questions, and it's still reasonable for us to ask those questions. So to summarise those arguments, reconstructions impose boundaries from an external viewpoint, so are not fit for the task of providing constructive or dynamical insights. They explicitly abstract away from the underlying physics, so we shouldn't expect them to provide insight into this. Principles are results of quantum theory elevated to the status of axioms, and so they don't provide additional insight into the results or phenomena. And carrying out reconstruction involves a choice of concepts and principles to privilege. There are a number of information theoretic reconstructions, and they differ in what are identified as the key features of quantum theory. And we don't have an obvious way of deciding between them. So it's not like we can say, oh, well, this is a better reconstruction, and therefore we should take more seriously what this reconstruction tells us are the important things. We have this choice of which concepts or principles we choose to privilege according to which route we choose to pursue. And so that doesn't give us motivation to privilege those things. So if I don't think that interpretation is afforded by reconstructions, what do we get? Well, I think that a useful feature of reconstructions is in providing explanation and understanding. And others agree. Various claims in both the physics literature and the philosophy literature. I think these are often not fully worked out or argued for, but I think it's interesting to see what the people that are writing these reconstructions or doing this reconstructive activity think that they're achieving through doing this. Hardy, for example, physics is primarily about explanation, and we can said to explain quantum theory more deeply if we give reasonable access. And we also see claims about understanding. And I just want to highlight this quote by Barnum et al. In particular, because it very much speaks to what I'll argue the role of reconstructions is in this context. So in order to gain a clearer understanding of quantum theory from this perspective, it's useful to contrast it with various fictitious alternatives. I don't know if that's supposed to be fictitious alternatives that are neither classical nor quantum. So can we get explanation through principal theories? And again, I'm sure many of us in the room will be familiar with the debates between, for example, Harvey and Oliver on the one hand, and Chris and Oliver, and James, I think you've written on this too, on the one hand, versus Balashov and Janssen and Lange, who argue that principal theories explain in virtue of the constraints that they impose. So my claim is that explanations can be had through both constructive and principal theories. And I make three progressively stronger claims to this effect. So I think that in the case where we don't yet have a constructive theory, we might settle for a principal theory explanation as a kind of best we can do for now scenario. Secondly, I maintain that even if we do have a constructive theory, principal theory explanations can complement constructive theory explanations and contribute to a wider network of explanations. And finally, and this might be more controversial, there are some contexts in which we might prefer a principal explanation over a constructive one. Interested to hear in the Q&A the extent to which people agree with that claim. Okay, so how can we provide a model of explanation or an account of explanation on which we can make these claims? And I guess maybe just to motivate that position, I think there is something to be said for taking scientists at their word when they say that the work that they are doing provides explanations and understanding. And so I'm going to go down the route of we can say that reconstructions are explanatory. Can we take these claims that reconstructions are explanatory? Can we give a reasonable account that fits with that? I guess the other move would be to say, well, no, they're just wrong. They are not explanatory because we should expect these particular features of our explanation. But I'm opting for the former route. So these are two views that I think get some of the way there towards identifying the roles that reconstruction can play in explanation. So Van Camp in 2011 claims that reconstructions explain by unifying phenomena, building on Kitcher's development of Friedman's unification account. So unification is held to be explanatory by reducing the number of facts that need to be accepted by using the same deductive patterns to describe many phenomena. But I think we can question whether reconstruction provides new or additional explanation on this account. Remember that we want to motivate explanation over and above that of quantum theory to be able to motivate reconstructions in this way. Our theorems and results that come from the theorems of reconstructions are also results of quantum theory. And so I think there's a question of what further are we getting out of recapturing quantum theory in terms of principles. Feline, I think, recognises this and provides a helpful development of Van Camp's account to suggest that reconstruction explains by identifying characterising properties of quantum theory from which phenomena can be deduced. So on her account, explanation requires showing how changing particular characteristic properties which are identified through reconstruction change the phenomena to be explained. So answering what if things had been different questions. But as far as I understand it, on Felline's account, there seems to be an appeal to an objective notion of characterizing principles. So it seems to almost be taken that in carrying out a reconstruction, there is we get closer to what is the right way to capture quantum theory. And as I previously argued, I don't think that's the case, because we have these multiple definitions, because we choose to recapture quantum theory in a particular way. As I've said, in the CBH case, the principles of the information theoretic formulation are equivalent to the corresponding theory. So we don't necessarily gain any further unification. And that undermines Van Kamp's question. And for black box reconstructions, again, the constraints on the correlations must be true in quantum theory, but they might not be as easily evident. And we might also question the scope of that kind of additional result. So I suggest that principal theoretic reconstructions only offer limited additional unification or answer more questions beyond ordinary quantum theory. But what they do is allow us to unify quantum theory in terms of the concepts, features, and relations of our choosing. And they also provide the ability to fix background factors so that we can define a particular set of W questions aligned with our interests. And the answers to those questions become more readily accessible. So how can we fit those claims and those helpful features of reconstruction into a model of explanation? So I think Van Frassen's pragmatic model of explanation is a good way to do this. Keep an eye on the time. Okay, so Van Frassen's model of explanation is based on the idea that pragmatic factors should be taken into account when deciding what counts as explanatory. And these pragmatic factors include facts about the interests, knowledge, and motivations of those receiving and or providing the explanation, and they also vary with the context in which the explanation is requested. So for Van Frassen, explanations are answers to why questions for a given context. So a why question Q is an ordered triple PXR, where P is a true proposition, X is the contrast class consisting of proposition P and its alternatives, and R is the explanatory relevance relation between proposition P and the contrast class X. And this contrast class and the relevance relation is determined by the context. So as an example of this, consider the question, why does the Earth orbit the Sun? On Van Frassen's account, the request for an explanation here is dependent on the contrast class that we're considering. So there's a kind of implicit contrast class in the question. So we might be asking, why does the Earth orbit the Sun rather than Alpha Centauri? Or we might ask, why does the Earth orbit the Sun rather than flying towards it? And we also have alternative answers for each of these contrast classes and alternative relevance relations. So we can answer the first question answer the second question in three different ways by using an alternative relevance relation. So we might say the Earth orbits the Sun rather than moving towards it because it also moves forward very fast. We might say the Earth orbits the Sun rather than moving towards it because of Kepler's law of planetary motion. Or we might say the Earth orbits the Sun rather than moving towards it because it follows the time-like geodesic of space-time curved by the presence of mass. So all of these are perfectly good answers, but they might be more appropriate for a given context. These might be the existing knowledge of the person that requested the question, but they might also be other things. On Van Frassen's account, we can also evaluate explanations. So if we take theory K plus some other scientific information and ask question Q with proposition BP and contrast class X, how can we evaluate answer A? So there's various things to consider. So one of them being the acceptability or the likelihood of being true, that is the probability of A according to K. We could also consider how the answer fares compared to other possible answers, including how much A raises the probability of the proposition compared with other answers, and also whether the answer is made irrelevant by other answers, for example, being screened off. So just to raise an objection to Van Frassen's account, Kitcher and Salmon argue that Van Frassen's account is too general, so rules too much in, and they suggest, as an example, the relation of astral influence. So the time t at which a person dies can be explained in terms of the relation r star in the position of astrological bodies at the time. So Woodward and Ross suggest that, in response to this, we can reply to this objection by requiring that the relevant background knowledge be scientific and using that to distinguish acceptable relevance relations. They take it that this is a deflationary account. I have no issue with a deflationary account here. I think it's perfectly acceptable to say this is a good explanation. This is a good scientific explanation because it appeals to the relevant scientific knowledge. But I do also propose a slight strengthening of Van Frassen's accounts. So I suggest a desideratum of stable covariance, which is that subject to contextual conditions, a change in explanandum varies predictably with the change in the explanans. And I think that would then address this counterexample of astral influence. I think would still allow sufficient generality for the account to be useful. On to a pragmatic model of understanding before I come back to what we can say about reconstructions on this pragmatic account. So how can we extend this model of explanation to a model of understanding? So starting with a bit of a kind of grammatical analysis of understanding, we often talk about understanding that P, understanding Y, Q, or understanding a domain D. And understanding why is particularly relevant for scientific practice. And there's various discussion in the literature about whether understanding why captures everything interesting to say about understanding more generally. I think that doesn't, my argument doesn't hinge one way or the other on that. We want to establish that reconstruction contributes some way towards understanding, and if we can establish understanding why, which I'll suggest we can, then that's all we need to do to argue that reconstructions can contribute towards understanding. So here's my suggestion for a pragmatic model of understanding, which is linked with Frassen's explanation. So consider agent S. On receiving a request for an explanation, that is a why or how question, S considers the context in which the request is received. S uses her grasp of scientific knowledge, including information and scientific theory, to propose an answer or answers. And S then evaluates whether or which answer is most suitable for the context-defined contrast class and relevance relation, using her grasp of this knowledge, which is coherent with her information in a particular scientific theory. A few points here. Note that this request need not be from an external source, so it might be that somebody's reading and asks themselves a particular why question. It's not, we don't need somebody to us and say, why is this, to have understanding. And secondly, I'm understanding grasping as knowing facts and the relations between them. So it might be the kind of common objection to claims about understanding is that if we try to capture them in terms of grasp, then that just pushes our question further onto what is grasp. But I think we don't need to be too concerned about that. I think we can give a sensible definition of grasp that still has the right amount of pragmatism and doesn't require some sort of special ability. And we can also give an account of understanding in degrees. So taking inspiration from...
Sorry, Natasha, do you leave something else on the previous slide? So that sounds like it's about explanation, about S having the capacity to answer explanation, to give explanations, but you didn't say what connected that to understanding.
Understanding is doing these steps.
It's being able to do those steps.
Being able to do these steps. So we can also define minimal understanding and increased understanding to give us an account of understanding in degrees. So I suggest that S has minimal understanding Y if one answer to a question is identified, which may or may not be suitable for the context. And then we can define understanding growing with an increased ability to carry out any of steps 1, 2, and 3. So for step 1, we can say we have an increased understanding with an increased ability to identify context. For example, having a knowledge of a wider range of contexts or appropriate contrast, class, and relations. For step 2, we could have an increased ability to use scientific knowledge to identify further answers. And for step 3, we can have increased understanding by increasing ability to evaluate answers. So we have these different dimensions on which understanding can grow. We can also consider ease of understanding. So certain activities can facilitate this. So one example would be exemplification, and I think this is particularly relevant in the case of Reconstruction. So exemplification allows us to give the answers relevant for a particular context. And exemplification being rendering more epistemically accessible by bringing to the fore in some way. We can also facilitate easier understanding through familiarity with the subject matter. So this might be gained through performing experiments or solving problems, using mathematical techniques, which then allows one to give a greater variety of different answers, and that contributes to steps 2 and 3. So before turning to how we can account for understanding through Reconstruction, I'll consider some potential objections. So firstly, we might think that this is already ruling too much in, that we need to be more careful in what we rule in and rule out of providing understanding. I think one thing to say, which I've already said, is I think we should take scientists at their word in what they say provides understanding. And if our current models of understanding rule out what scientists say provides understanding, then perhaps we're being too narrow with our definition. And we can also appeal to scientific background knowledge in a similar way that Woodward and Ross respond to the objection to Van Frassen's account. And we might also think that this account doesn't sufficiently capture the notion of understanding as a special ability. But I think on my account, there are multiple abilities involved. So recognizing context, evaluating answers, and accessing and manipulating scientific knowledge. So whilst these may be pragmatic, I think they're perfectly suitable abilities that we would expect of someone having understanding. And finally, we might think that somebody could just parrot an explanation and then be said to have understanding. But I think, as above, we can appeal to those variety of abilities that are required to demonstrate that simply repeating an explanation isn't sufficient to say that somebody understands something. Okay, so last section now, explanation and understanding through Reconstruction. So I claim that the Quantum Reconstruction Programme provides a tool through which to seek answers of a particular kind for a given context. One can fix the contrast class by considering a particular set of background theories from which the explanandum, some aspect of quantum theory, can be derived, and we can choose the relevant relation. We can choose the relevance relation to identify the salient answers. And reconstructions facilitate understanding by broadening the context in which answers to questions can be given, as well as rendering it easier to identify the appropriate explanans. And the relations that are invoked in Reconstruction are not about underlying mechanisms or phenomena, and the principles don't need to be foundational, they don't need to have any kind of metaphysical impetus behind them, but this doesn't mean that they're not explanatory. We can still say that they're explanatory if they exhibit stable covariance and are part of a scientific theory. And it's important to say, though, that these explanations don't replace other answers that make use of other relevance relations, such as constructive explanations, but they supplement them to provide a broader explanatory toolkit. So which contexts might we request these kinds of explanations? Well, as I've already mentioned, in cases where we don't have a constructive explanation, an explanation through principles might be the best we can do for now, and it's still something. I think this goes some way towards resolving the principle constructive debate, as I previously mentioned. And we might also want to be able to summarise a theory in brief to present it to a general audience. So we might want to appeal to particular information theoretic constraints to explain some phenomena, for example, why we might expect to speed up in quantum computing or something like that. We might be interested in operational possibilities for developing new technologies, and we might also want to know the boundaries of quantum theory to propose new experimental tests. So I think there are a variety of questions where we might want an explanation of this form, of a principle form. So let's take a closer look at those case studies. So in the context of the black box approach, the central why question is why are quantum correlations bounded by the Cyrilson bound? And on Van Frassen's model, the question here, the relevant question would be, why are quantum correlations bounded by the Cyrilson bound in contrast to other non-local correlations? And black box principles can offer alternative explanations to those offered in ordinary quantum theory, which might privilege different concepts. So for the case of the information causality principle, we could give derivations in terms of sending information or of properties of entropy measures or uncertainty measures in those theories. So here is an example of the kinds of the kinds of answers to questions of a particular kind that we can give on the black box approach. So our contrast class is the strength of non-signaling non-local correlations, and captured with these P's in terms of the CHS8 sum K. The relevance relation is the constraint imposed by possibility associated with performing communication tasks. And these abbreviations here correspond to the previously mentioned principles on the black box approach. So non-trivial communication complexity, non-trivial probabilistic. Oh, I've explained them now. I don't need to be trying to remember what they are. And each of these, as I mentioned previously, each of these achieves a different level of success in how much of the correlations that are not quantum are ruled out using them. Give a different proposition, to correspond to a different proposition. But for example, the question would be, why is the strength of correlations bounded by one rather than a different strength in terms of a constraint imposed by possibility associated with performing a communication task? And the answer would be non-trivial communication complexity. So these might be thought of as fairly limited questions, but nonetheless, I think they do go some way towards capturing the understanding and explanations that the black box approach provides. So considering information causality in particular, information causality provides an answer to the question why the Cyrilson bound in the context of possibility of performing computational tasks from amongst a class of theories with non-signaling, non-local correlations. We can also consider whether we need to worry about those earlier concerns that I flagged up. But I think that we don't, these earlier concerns don't preclude information causality from being explanatory and from contributing to understanding. So principles don't need to be foundational to be explanatory. It satisfies the relevance relation of being about the possibility of performing a computational task, and it also satisfies the stable covariance principle. And so it provides understanding by answering why questions. Because of the feature of my account that says that evaluating answers contributes to understanding, the earlier discussion about alternative derivations of information causality from properties of uncertainty measures also contributes to understanding, because in considering those kinds of questions about how different explanations relate to one another or are screened off, we make this kind of evaluation. So this goes some way towards motivating further work on these kinds of principles, despite the fact that we know that they may not be successful. On the CBH reconstruction, again, we can define our proposition, answer, contrast, class, and relevance relations. And you can see here that we have a symmetrical explanations. And so kinematical independence is explained by no signaling if we're requesting an information theoretic constraint, and similarly for the other two. And in the reverse, if we are looking for a constraint imposed by theorems of physical theory, then we can say that no signaling explains kinematical independence. I don't think we need to be concerned about this symmetry because we're talking about a pragmatic account and which direction that did I say asymmetry? I don't think we need to be concerned about that symmetry because it depends on the relevance relation that we are requesting our answer to refer to. So on the CBH reconstruction, we can answer, by adopting the information theoretic reconstruction, we can answer why questions about quantum phenomena from the perspective of information theoretic constraints. And we also learn more about how the characteristic properties of quantum theory relate to information theoretic tasks. And again, we don't need these principles to be law-like or foundational or causal to offer an explanation. We gain understanding by uncovering these relations, or even just drawing attention to these relations, so exemplifying them. And again, we can appeal to the previous discussion of the concerns to contribute in itself to our understanding. So screening off no bit commitment is an example of evaluating an answer. The screening off of no bit commitment is an example of evaluating our answers. And so again, this kind of continued discussion about what the principles are achieving also builds understanding. Back to the measurement problem. So you might question, can CBH reconstruction address the measurement problem, and how can we capture that earlier discussion around interpretation in terms of this account of understanding? So here's a question related to the measurement problem that I think CBH can answer. So why is the change after measurement in probability distributions, why is there a change after measurement in probability distribution over measurement outcomes compared to other ways in which the probability distribution might change? And we're requesting an information theoretic constraint. Well, the answer would be no signaling, no broadcasting, and maybe no bit commitment, which then entail the Hilbert space structure. And I think that's still an explanation. It just might be for that particular relevance relation. But what we can't answer is a question like why is there, oh right, okay, sorry. I find these I made these tables and I still find them a bit challenging to interpret. But we can't answer why is there a change after measurement in probability distribution over measurement outcomes compared to theories with different dynamical equations that give rise to the same probability distribution at time t, where a relevance relation is a dynamical description. The answer there would be some interpretation, and can't answer that using the CBH reconstruction. And again, I think that's fine. Our reconstructions can give us understanding and explanation in these particular contexts, and we don't need them to provide understanding and explanation in all contexts for all relevance relations. There are also other activities within the Reconstruction programme that contribute towards understanding. So we've already heard that reconstructions can also improve our understanding by providing more explanations and making the context class explicit, and by making certain facts and connections more epistemically accessible, by obscuring irrelevant details and allowing a change of context so that relevant facts and entities for a particular context are brought to the forefront. Again, that's the exemplification property. But in addition to this, just playing around with reconstructions also generates familiarity with mathematical tools and concepts. And we can draw an analogy here with a show that question in an exam, for example. Okay. So in conclusion, the insight offered by principal theoretic reconstructions is to some extent a matter of perspective, but this doesn't prevent reconstructions playing an epistemic role. On a pragmatic, pluralist model of both explanation and understanding, that should say, according to which explanations and understanding are accounted for in terms of answers to why questions appropriate for a given context, reconstructions genuinely do contribute. Thank you.